Okay, good morning, everybody. We're going to continue talking about search trees today. But as we continue to explore the idea of a search tree, we're going to start to back off from the binary part. That is, it's going to turn out that there are certain advantages to thinking about constructing a search tree that's not restricted by a strict two-way decision about how the tree is to be navigated. And we're going to look at some approaches to that today, some of the implications of those approaches, and think about some of the pros and cons and trade-offs involved therein. So we're going to think back to a fairly classic example of building a binary search tree that we've worked on quite a bit so far, which is the idea of values being entered roughly in sorted order already, and how with a basic binary search tree, that tends to lead to a pathological data structure, the degenerate tree that becomes just a big long twig, so to speak. And so an approach that we've looked at for addressing this, we've talked about briefly, and we kind of went over in the lab with the idea of using tree rotations to balance it out. And we talked briefly about the idea of the red-black scheme as a means of accounting for whether a rotation is needed. I'm going to show you a somewhat different way to think about it now, though. So we might imagine beginning by adding, the node A to our tree. And from here, we could then add a node containing the letter B. And of course, that would go to the right, since B is lexicographically later than A, alphabetically later than A. But already, even just getting to this point, we recognize, there's a sense in which this tree is out of balance, right? It's got something over here and nothing over here. And just looking at it, we might think, well, such is the way of things, right? There are only two elements, and if we're building a binary search tree, somebody's got to be the root, and then somebody's not. So here is maybe a more extreme solution motivated by the idea of saying the tree must always absolutely, positively, no questions about it, be balanced. So what we could do is relax the constraint that a node only contains one value. So we can imagine adding B as kind of a co-inhabitant of the root node. And so what this buys us is that the tree is balanced, which is great. And just looking at it, it's like, well, it's not so much more effort, right? I mean, now we have to do two comparisons at the node instead of one. But that's not so bad. But then we imagine adding another value, like C. And at this point, well, this is a remarkably peanut-like node. Anyway, at this point, we might just kind of have to put our foot down and say enough is enough. That is, if we just allow an arbitrary number of values to be stuffed in a node, we might as well just have an array and call it a day. So imagine that what we've done is said, yeah, you can stuff maybe one extra value in a node, but that's it. And if you try to stuff two values in, then we need to rethink things. So here's how we might rethink things. Now that this has three values in it, we can construct a perfectly balanced binary search tree from it. What would that look like if I constructed a perfectly balanced binary search tree using these three values?
B would be your root, and then A on the left, C on the right.
I agree completely. So we have B at the root, A is over here, and C is hanging out over here. And so what I have done is I have maintained my constraint that the tree must be perfectly balanced. Of course, we can't start a scheme like this without figuring out how to torture it further. So let's do that. So let's imagine we add D to the tree. Well, D is greater than B. So we're going to go to the right. And then we get here, and we're like, C has space. So we're going to add D over here. Okay, C didn't have a lot of space, but it had enough. All right, but why stop there, right? So we're going to add E to the tree. So E turns out to be greater than B, and it comes down here, And it turns out this node is kind of busy, right? It is out of space. So we know E needs to get in there somehow. So we're going to have E just kind of hang out over here on the side for the moment. And the way that this style of search tree works is that additions to the tree always happen bottom up instead of top down, as we've been accustomed to doing with the binary search tree. So in other words, we start stuffing things in the leaves, and when the leaves get too stuffed, they push upward. They shove things up the tree to see if they can be accommodated. So, looking at C, D, and E, which value do you all think we might shove back upward? So why C?
You have two values on each side. You have AB, and C would be your root, and D would be your right.
So that's reasonable. It's not what we're going to do, but it's reasonable. And it's reasonable because we preserve the constraint that we have no more than two values in each node, and the tree remains balanced. Now, what would it look like in contrast if we were to shove D upward? Kind of weird. What's weird about it, Caleb? Let's see what we can do. There might be another constraint we can relax. I'm going to take D, actually, and I am going to put D up here, like that. But now here is the fun part. I am going to give C its very own node over here, and E its very own node over here. So let's look at what we've achieved with this particular scheme. If I come into the search tree, because I have two distinct values here, I have conceptual space for 3 children. So that's another constraint that we hadn't quite relaxed yet, but which we're going to relax now. Since I've got space for a 3rd child, the strategy I want to look for is to ensure that the left child is always less than the lesser of these values. The middle child should be a value that's between these, and the right child should be greater than the bigger one. So, well, let's not stop here. It's time to add F. So F comes in, and F is going to go right there. And of course, now things are going to get really bad. What am I likely to add now? G, yeah. So G is hanging out over here. It had to go right. It was bigger than D. And then it gets down here, and this node is looking pretty busy. So what it is going to do is shove a value upward. What value do you all think it's likely to shove upward? F, good. So F is going to come back up here. So let's imagine what this is going to look like for now. I've got E and G hanging out here. B and D are up there. And I just gave this poor node an F, metaphorically speaking. What's it going to have to do now? What happens at this point? What's our poor root going to do? It's going to what?
Are you going to push D up?
We're going to push D up. Yeah. So D gets to ascend. So let's imagine what that resulting tree is going to look like. D moves up, and there's nowhere further to move up, so D is now solo. And now what we'll do is we're going to split up this node as well. So, oops, still erasing. We're going to have B over here and F over here, and these guys are going to go kind of like that. And then we're actually going to come down and split this thing up. And then F becomes its own, and bam! We now have a perfectly balanced search tree that just happens to look binary for the moment. As you can imagine, as we keep adding stuff, the leaves get filled up. They promote values upward. Those interior nodes fill up. They promote values upward. And once there are too many values in the tree, then we start splitting things up again. So this type of search tree is known as a 2-3 tree. It's a 2-3 tree. Why 2-3? Because sometimes a node has 2 children, and other times it has 3. This was a naming masterpiece, you might say. Okay. So 2-3 trees are a valid solution to the problem of building a search tree. In terms of the asymptotic time complexity, it tends to work out roughly the same way. A difference being that considering the number of items versus the number of levels, right? The number of levels might be the log base 2 of the number of items. That's sort of the biggest it can be. But it might actually be even smaller than that. It might be based on the log base 3, right? Because we've got 3 children coming down. But as we've discussed, whether it's the log base 2 or the log base 3 doesn't really matter very much when we think about the idea of big O and the asymptotic time complexity. Why? Because the base of the logarithm is merely a constant, right? And so since it's a constant, we can still say that the height is bounded by the log of n for some constant base n, clearly greater than 1. So the 2-3 tree is an effective solution to the problem of building a binary search tree. So why do people keep coming up with new schemes for this sort of thing? We've talked about red-black, we've talked about the 2-3 tree, and there are others. I'll just mention a couple. There's what is known as the AVL tree. The AVL tree was the first automatically balancing binary search tree that anybody came up with. It is pathologically complex to implement. It is a binary search tree that maintains strict balance, no more than 1 level below or whatever. But the trouble with it is to get to that point, you wind up having not only single rotations, but double rotations. It's just astonishingly complicated. Kind of a simple and fun scheme is known as a splay tree. And the idea of a splay tree is that every time you do a search, you actually do rotations in the tree to bring whatever node you were looking for up to the root. So the motivation behind a splay tree is if you do a search for a particular value once, you're likely to look for it again. And so you keep things that get looked for a lot near the top and things that are looked for less often near the bottom. And as you yank them up, you rotate things to keep it balanced along the way. So splay trees are kind of a fun idea. But all of these actually run into a fairly severe hardware limitation that constrains their performance in an important way and leads to what we might think of as, at least for now, the ultimate approach to search trees. So first, let me talk about the limitation, and then I'll talk about this ultimate approach that is generally speaking, what's getting used in practice at this point. So the limitation is based on issues in the memory hierarchy of the computer. So when I say memory hierarchy, what I mean is until now, and actually after today, you're going to go right back to this little illusion. But until now, we've thought about a memory access is just a memory access. That is, if I want to read some value in memory or write some value into memory, it's this straightforward linear process. The memory address is a binary string that feeds actually into a multiplexer for circuit aficionados. And that multiplexer figures out that's where the data goes, and the data goes there. And that's the memory circuit at its most simple. Unfortunately, this scheme, which worked great for decades, no longer actually works very well. And the reason it doesn't work very well is that our main memories have gotten too big. What do I mean by too big? So, anybody, the last computer you bought, how much RAM did it come with? 16 gigabytes of RAM. So, Caleb, it came with 16 gigabytes of RAM. What does that mean to you? It does, but how much stuff? When we think about this term, gigabyte, how much stuff is this saying? If I say giga something, what do you all think that means? 10 to the 12. It's actually 10 to the 9, but close enough. Yeah. Yes, 10 to the 12, that's tera. Yeah. So let me rephrase that, right? Giga is a prefix denoting a billion. So 10 to the 9th. Tera denotes trillions, 10 to the 12th. So Caleb's computer has 16 gigabytes of RAM. So roughly speaking, 16 billion bytes, and each byte is 8 bits of storage. Now, on a modern computer, instructions actually don't even process data at the level of a byte. So the CPU typically processes data not as 1 byte at a time, but as 64 bits or 8 bytes at a time. So like when it says that you have a 64-bit CPU, that's saying the unit upon which the CPU does math is 64 bits in size. This is generally a good thing, right? Because if it can do that, it means that each computation is, in a sense, more efficient. It's getting more work done than otherwise. But still, 16 billion bytes. Now, just pick on Caleb because he volunteered. When you bought this computer, what was the gigahertz of the CPU? 2.6 gigahertz. There's giga again. What do you all think that might mean? Gigahertz. Definitely time. I'm feeling time. It's a frequency. Good. What do you think, Jake, it's a frequency of?
I guess how many times the CPU will keep doing something.
It's how frequently the CPU does something. That is correct. Hand waving a little bit, but yeah, it's how frequently the CPU does something. Would you all care to guess the frequency with which the CPU of the first computer I owned back in 1982 did something. The Commodore 64.
20 hertz.
That is such a generous, oh no, 20 hertz, okay.
Yeah.
That's an underestimate, yes. It was certainly faster than that. It was 1 megahertz. Okay, so from 1982 to 2019, 37 years, we've gone from major commercial grade computer doing 1 million things per second to a standard commercial grade laptop doing 2.6 billion things per second. Now, just imagine this if you will, right? I have been actively writing software for that entire time span, 37 years. I'm not that old a person. But in that time, we've gone from consumer grade CPUs doing 1 million operations a second to 1 billion. I want you to just let that soak in for a minute. The amount of technological improvement here is astonishing, but it has come with a subtle and painful cost. That subtle and painful cost is this: packing 16 billion bytes onto a circuit board has actually proven kind of difficult. Difficult in the sense that the CPUs have gotten so fast that the time necessary for the electrons to get from the CPU to the outer reaches of this memory and back is far slower than the time for the CPU to perform its calculations. Note that this is an intrinsic problem. There is no technical solution to this. One way you can think about it, right, is imagine that that you've got the CPU here like in the middle of a circle, and then the main memory is like out here surrounding it. So if that main memory is, I don't know, n bytes, an electron has to travel a distance proportionate to this. What's the minimum such distance going to be, assuming that everything is like perfectly packed? Hint, I drew a circle. The radius, right? So in other words, it's going to have to travel at least a distance proportionate to the square root of the number of bytes on average, right? So without getting into the hard numbers, I mean, we could do that if we really wanted, but the bottom line is this round trip travel from the CPU on back introduces stalls in the CPU's ability to process data. If the CPU has to go to main memory, it might have to pause as many as 50 or 100 cycles just to wait for data from main memory. That is devastating for performance. The solution, which generally works pretty well, is to have a memory hierarchy. So, just picking on Caleb again because he's been so forthcoming with data about his computer. When you bought this computer, what size cache did it advertise? Oh, that's okay.
I'm searching currently. Would that be a hardware resource list?
It might be, yeah, could be. Oh, that's okay. It was maybe a few hundred megabytes, I would guess. So what do we mean by this term, cache? Well, here's the big idea. And it's similar to the big idea of a splay tree. Namely, data that you access is likely to be data you will soon access again. That is, in practice, a program does not uniformly access every one of those 16 billion bytes of RAM. Like, it's not a uniform probability distribution. Some parts of memory are more popular than others. So what we do is we have a small amount of RAM located physically near the CPU. And whenever we perform a memory access, we actually bring into the cache not only the contents of that address, but a lot of stuff nearby it. Why a lot of stuff nearby it? Well, let's think back to what's the single most basic data structure we kicked off the semester with? More basic than that. The array. Good. Right. And what is an array? I mean, it's a thing and it's got values. What are some properties of an array? Indexes, right. An array allows us to have fast indexed access to its contents. And the reason we get fast indexed access to its contents is that the array is simply a thin abstraction on top of the main memory of the computer itself. So if I've got two elements in an array, one's at index 0 and one's at index 1, they are next to each other in RAM. And the thing at 2 is next to the thing at 1, and it's like 2 spaces away from the thing at 0. So an array is just a slice of the RAM of a computer. Arrays being the popular data structure that they are, what you do is the cache, when you access some area of memory, there's a pretty good chance it's actually part of an array. And here's part of how you can think about it. If you write a program, what part of the program is likely doing the most work? Where is the CPU probably spending most of its time in a program? What kind of language construct probably consumes more CPU than anything else? Phrased differently, if your program were running and you were to stop it, what type of code would most likely be the thing that was stopped? If you think about the different ways a program can be put together.
Traversing a data structure.
Okay, good. Traversing a data structure, looking for stuff. Specifically, traversing a data structure either via iteration or recursion tends to involve a loop. In general, if you stop a program at any point, odds are you have stopped it inside a loop, right? If you write a program that has at least one loop, and odds are if you write a program that has at least one loop, I think we would generally agree. If you stop it, it's probably in the loop. And if a program is in a loop, there's a pretty good chance it's traversing a data structure, as Caleb correctly points out. And if it's traversing a data structure, there's a really good chance that that data structure, deep down in some way, is an array. And so a hardware designer thinking about building a cache can construct the circuitry such that if I access a memory location, I also get its neighbors in the cache on that same fetch from main memory. You know, circuit-wise, it's just as cheap to grab 50 things from RAM into the cache as it is to grab one thing from RAM into the cache. Actually, they're going to grab a lot more than 50 typically. But that gives you a sense as to the magic here. So if I'm accessing an array element, and I have what's called a cache miss, that is, it's not in the cache, my poor CPU accepts its stall, it twiddles its thumbs for 100 instructions, the data gets into the cache, but now the next time through the loop, it's already there. And it can just truck along and do really well, performance-wise. So what this means, And this is something that has changed over the 37 years that I've been an active software developer. Okay? Is that there is a hardware prejudice, so to speak, against data structures that are linked. And the reason for this prejudice is that because each of these links is to a memory location that cannot be presumed to be contiguous with its predecessor, every time you traverse a link, you're probably going to miss in the cache. And that can introduce a substantial performance slowdown. So, what's this have to do with trees? It turns out everything. So trees are a great data structure for maintaining a body of data in sorted order. In fact, in principle, you actually can't do better than a tree for this, okay? But we can think about how might we optimize our trees for best overall performance. Given this idea of a cache, and given the idea that arrays are cache friendly. Arrays and caches like to work together. So here's the solution. Minimize the number of tree nodes and also minimize the number of tree levels. So what is it going to look like to do that? If I'm going to minimize how many tree nodes I have, and I'm going to minimize how many levels I have, what I am maximizing is how much data I'm putting in each node. So if you think of each tree node as containing an array of values, and between each pair of values, there is a child pointing at a node with another array. What we have done is we have taken the 2-3 idea and turned it into what you might think of as an n plus 1 idea. And so this concept is what is known as a B tree. It's what is known as a B tree. So the idea of a B tree is it's perfectly balanced, like a 2-3 tree, and it works just like a 2-3 tree, except that you have some large constant representing the maximum number of values in a node. And that constant plus 1 is the number of children that that node is going to have. Now, just thinking about this probably makes your head hurt a bit. Just imagining the complications involved in splitting and reuniting and blah, 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 blah. And you would be right to feel the pain. It is painful to do. There are interesting questions about what you do at a specific node. So, given that the number of values in a node is constrained by a constant, in principle, it can be reasonable to do an outright insertion sort to keep those values organized. So inserting one value in sorted order is linear time, of course, but if it's linear in a constant, even a big constant, given the savings we're getting by using arrays, it can actually be worth it. So essentially what a B tree has to balance is the O of k for an insert versus the memory stall. So in other words, this is something that has to be determined through experimentation, right? there's no straightforward analytic way to work out what that trade-off looks like. You actually have to optimize it for a particular combination of hardware, software, and so forth. But the principle is nice because you can see what the trade-off is and what knob you can tweak to maximize the performance of your tree. Now, the B tree was specifically designed with this kind of scenario in mind, where each link jump is an expensive operation. But seemingly contrary to what I was just talking about, it was actually invented a long time ago, actually in 1970, long before this disparity between CPU speeds and main memory came about. What motivated its invention in 1970 was actually implementing databases. That is, we had a memory hierarchy there as well. The memory hierarchy with a database, though, was a little different, although the concepts wind up being remarkably similar. You had RAM, and RAM was good, but RAM needed to get data from a hard disk. And the hard disk is, of course, slow. Well, you might think, why am I so prejudiced against hard disks? Why am I blaming them for being slow? Well, much like an old-style phonograph player, a hard disk has a physical read-write arm that must be moved to a specific location on the disk in order to read data from it. So even if you're dealing with, say, some pathetic 1 megahertz CPU, which in 1970 would have been fairly state-of-the-art, compared to physically moving a read-write head, it is waiting an eternity for a disk access. So B trees were developed for database organization such that they could visit the hard disk rarely. Each link in the B tree for a database is a request to disk. And so then they read in a bunch of consecutive sectors from the disk back into RAM, which even with linear search and insertion, given a constant bound, is a lot better than waiting on the read-write head to perform its business. So to this day, databases are typically built using B trees. And that's essential, especially for indexing the databases, for indexing. This is what databases rely on to be fast. Now, for insert, yeah, you kind of have this linear thing going on in terms of that constant. But for search, you can actually perform a binary search in a node to figure out which direction you're going. So in a sense, that's not so bad. So the B tree tends to be the kind of ultimate search tree in a way that it wasn't 3 decades ago because of this increasing divergence between RAM and the CPU. But it's always been the state of, well, not always. Since about 1970, it's been the state-of-the-art means of implementing an indexed database that's making use of a hard drive. Cool. Any questions about any of this so far? Okay, so there's another direction we can take this idea. The idea of a tree that has lots of children. And so I'll start on this idea today. We're going to talk more about this on Monday, and Tuesday, of course, we'll get to implement this. But this idea is motivated by the problem of text prediction. Specifically, text prediction based on a prefix. So actually, even in the time that I have been teaching this particular data structure, text predictors have gotten even better than before. But at its basis, you can conceptualize text prediction in terms of a prefix. That is, you start typing some letters, and then the predictor might say, here are all the possible ways to complete this, and kind of a drop-down menu, and then you pick one of these possible completions, right? So to implement this idea of text prediction, once again, we can use a tree. But we can think very differently about the tree here, because what we're going to do is actually spread the key out all the way down the tree. So we're not even going to have an entire key in one node. Instead, starting at a node, we're just going to have the first part of the key. And as we descend in the tree, we might have more and more of it. So here's, a way you could think about it. Let's imagine that I have put the following strings into my tree. Apple, ant, bat, bar, back. So at the top level, we don't have any letters, but associated with each link, that's the A link, that's the B link, the A child and the B child. Then from the A child, we've got a link that then ends in NT, and then we've got a link that ends in PPLE. And of course, you could imagine extending these out if there were more contenders, as we're about to do. Oh, whoops. Let me slightly change this list. Bat, bar, and born. Yeah, there we go. So then here we have an A link, and then here we end at ORN, and then here we end at T, and here we end at R. So you can imagine starting at your root and traversing this tree to reconstruct a stored value. So you start here. I want to know what's everything that starts with A. Well, I can just ask this subtree, give me all of your descendants. And that list of descendants then populates my drop-down menu for my autocomplete. If I type the letter B, as for all your descendants, well, I'm going to get bat, bar, and born. But then if I type in A, I just get bat and bar. And if I type in O, I just get born. Just like that. So this is a pretty cool idea. In fact, for strings, it's kind of difficult to do better than this. And here's what I mean. What is the tree height for this arrangement? How do we bound that or think about binding that? How deep is the maximum depth I have to go? Yeah, Elijah. The different endings for the starting letters. Yes. Or phrased slightly differently. Let's say I've got some value K. K is the maximum term length. I never have to go deeper than K to find a value. Now here's the really amazing aspect of this. Would you all say there is any relationship between K and the number of terms I insert into the tree? What relationship is there between those, if any? is there a relationship between these? And think in the broadest possible sense. What even vague ideas might you have about a relationship between these values?
Well, if you have a long term, you're going to have a bigger N.
Well, couldn't I have like a 50-letter word and have it be the only thing I insert? Couldn't I have a 50-letter word that's 50 among a billion words? So I'll pose the question, is there any relationship between them? Not really, right? So this is a whole other category of thinking about the time complexity compared to what we've been looking at. We can build this type of tree in a way that doesn't even have its performance depend on the total number of items. Now, it depends on some other aspects of those items. For instance, this N may well influence how many children you're going to have at a node, right? The bigger N is, the more children you're going to have, and you're going to have somewhat more work at a given node. But it's kind of infinitesimal in comparison to other things we're thinking about. Here's what I mean. Let's imagine that you're strictly, handling strings, right? So if you're strictly handling strings, just to keep things simple, we could posit that the maximum number of children per node is 26. To get to 26, of course, I'm assuming lowercase. I'm assuming no punctuation or spaces. And I am definitely assuming no Chinese, right? But it gives you a way of using a constant to bound the maximum amount of computation you're going to have to perform. Now, again, much as with the B tree, this will wind up necessitating some kind of insertion scheme, but even then, not necessarily. So you could just have every node automatically have a 26 element array that's indexed using the Unicode value for the letter, right? And so then that's constant time to insert and to look up. If you can't readily bound it, but you just know it's going to be relatively small, then you can insert in sorted order and do binary search. But again, it's going to be on a very tiny n compared to the number of things that you're adding. Note that this is less flexible than a binary search tree. It's less flexible in the sense that a binary search tree only requires that the data you insert be totally ordered with comparisons. What this type of tree requires is that your data be built in this lexicographic style. So you have to have something that can be interpreted as a string in order for this to work. Not all data is like that. For things that can't be interpreted as a string, the binary search tree is theoretically as good as you're going to get, and the B tree is theoretically similar, maybe practically better, but it's still all the same kind of thing. This is a different kind of thing that puts you in a whole other category of efficiency. And so this type of tree is known as a trie, T-R-I-E. And so a trie then, also known sometimes as a prefix tree. And yeah, if you really, really want to, you can reverse the letters and make it a suffix tree. But you kind of have to start on one end or the other, to make this work. But this is a pretty amazing data structure for sorting and searching on string keys. And so our lab on Tuesday will be building a text predictor with one of these. And on Monday, I'll go over in detail how we're going to implement them. See you then.